bachelor's degree from the mechanical engineering department at Virginia Tech. He participated the UGG program, right? So this undergraduate, graduate, program. He started working in my group about a year ago. He was working on the design and the testing of a bubble generator for molten salt, surrogate fluid. So today he's gonna defend his MS thesis. So the process is, Quartz, for you, you will have about 45 minutes to present your research. Then after your presentation, the general audience can ask questions. So after that, the general audience have to leave the defense. So the committee members will stay and ask questions. After the Q&A session, the committee member will stay and discuss your defense. So you will have to step out for, I don't know how many minutes, typically 5 to 15 minutes. Then we will ask you to come back and tell you the results of the defense. All right. So do we have any questions?
No, I think we should proceed.
Okay.
Yep. Excellent.
Yeah. So by the way, I think during the defense, the committee members can ask questions, but the general audience, please, your chance to ask questions should be after the presentation. Okay. All right. Without further ado, Quartz, the floor is yours.
Excellent. Thank you, Dr. Liu. All right. So hello, everyone, and welcome to my thesis defense on the design and testing of a bubble generator for molten salt surrogate fluid. My name is Quartz Breeden. I work in the multi-phase flow and thermal hydraulic laboratory under Dr. Yang Liu. Over the course of this presentation, I will give you an introduction on why my research is needed. Then I'll go into a background on what I learned from my literature review, walk you through my design and fabrication process for the injector. Then I'll show you how I tested it, the results that I got from that testing and data processing. Then I'll show you how I modeled those results to make a novel microfluidic injection model. I will then wrap everything up with a conclusion. In modern day, we have a growing need for energy. And the way that we're producing that energy now is by burning fossil fuels by and large. But there's new evidence that suggests that releasing carbon into the atmosphere has detrimental effects to the environment. And burning fossil fuels emit a lot of carbon into the environment. In addition to this, fossil fuels are not very safe, and they cause a lot of deaths per kilowatt hour of energy produced, or relative to other energy sources like solar, wind, and nuclear energy. However, for solar and wind, they only work when the sun is shining or the wind is blowing, so they're not very reliable for powering the grid. So when neither of those are happening, you have to use backup generators. And this is where solar starts to emit carbon, which is very counterintuitive. So what about cost? This table shows you how expensive it is to produce energy per kilowatt hour. As you can see, burning fossil fuels is quite cost effective, but applying a carbon tax of $15 per ton of CO2 emitted to the environment makes these a lot less viable. And this is where nuclear really shines, because it doesn't release any carbon into the environment. With the metrics that I've said so far, nuclear seems like it's the clear winner here. But there are a couple very common reservations that people have for using nuclear. That being the fact that it has waste. So once this fuel is burned, it creates large volumes of waste that we need to figure out some way to deal with. And it also, in order to power these nuclear reactors, we have to mine fuel. So people have reservations about it being renewable. Both of these reservations could potentially be addressed by using breeder reactors. Breeder reactors make use of fertile elements like uranium-238 and thorium-232. These isotopes are a lot more common compared to fissile isotopes like uranium-235, which is conventionally used in light water reactors. So when you bombard these fertile isotopes with neutrons, they create a new isotope with a greater atomic mass, which is unstable. This isotope will then undergo 2 beta minus decays and create a fissile isotope. Fissile isotopes like plutonium-239 and uranium-233, when interacting with a neutron, there's a high probability that it will cause a fission. So this one isotope, this one nucleus splits into 2, creating 2 atoms, releasing a lot of thermal energy. And this thermal energy is harnessed to create electricity. So breeder reactors can come in all sorts of shapes and sizes, but within this study, we're focusing on molten salt reactors. In the molten salt reactor experiment, there are these gaseous fission products like xenon-135. Xenon-135 is a very powerful neutron poison, and it is dissolved within the salt in the molten salt reactor. And so when a neutron poison is dissolved within the coolant, it decreases the reactivity of the core, decreasing your ability to produce power per amount of neutrons within the core. And this is a very powerful metric, and it's a way of measuring the efficiency of the reactor and the efficiency of using that fuel. So the way that this xenon-135 is removed from the coolant in the molten salt reactor experiment is within the pump bowl of the primary coolant pump. So we bubble very small bubbles of helium through this coolant, the molten salts at 600 degrees Celsius. And since there's no xenon within that clean helium bubbling through, and there is a certain amount of concentration of xenon within the salt, that xenon naturally diffuses into those bubbles. And once those bubbles reach the surface, we're able to purify the xenon out in the off-gassing system. So it's important to study the way that these bubbles move. It will give us information on the safety of the reactor. Having bubbles within the core affects the reactivity of the core. So we really want to know how these bubbles move. But it's really hard to study that within this actual pump bowl for 2 reasons. It's at very high temperature, and it's also just putting instrumentation within the pump bowl would decrease its effectiveness. Sir. Oh, am I not? It says I'm screen sharing. Can the people online can't see it?
You mean the screen or the cursor?
The slides.
We can see the slides.
Yeah.
Okay. Sounds good. So this is where my studies come in. We want to create a surrogate fluid that can operate at room temperature that produces bubbles that behave very similar to the ones that are found within this pump bowl. So we can have very accurate data on it. So the way that we match the behavior of these bubbles to the way that they behave in the molten salt reactor is by defining 3 important dimensionless numbers of that bubble behavior. These being the Reynolds number, the Eötvös number, and the Molten number. The Reynolds number relates the inertial forces of each of the bubbles to the viscous forces of the fluid surrounding the bubbles. The Eötvös number relates the gravitational forces of those bubbles to the surface tension of the system surrounding it. The Molten number is very similar to the Eötvös number, but it doesn't take into consideration the bubble geometry. So again, it's the gravitational forces of the system divided by the surface tension forces in the system. So we can define these 3 dimensionless numbers knowing the properties of the fluid in the molten salt reactor and the size of the bubbles in that reactor. So if we can find a place on this map with the Reynolds number being on the vertical axis, the Eötvös number being on the horizontal axis, and these striations being the log of the Molten number. So we can look at the range of temperature that the molten salt reactor experiment operates under, and look at also the size of the bubbles that are produced in it, and we can define those three-dimensionless numbers and get a range. So this red box is our target for creating an experimental system. So the fluid that we decided to use for the liquid in this system, for the surrogate fluid, is a mixture of glycerin and water. This was used because it can be operated at room temperature. It's very inert, and we have a lot of data that show us how the different fluid properties of this liquid change with differing concentrations of the glycerin by weight. So you can see on these three graphs the viscosity, the surface tension, and the density. These three properties are what define those three-dimensionless numbers. So we get a range of the Molten number, and we first look at that because it doesn't look at the bubble geometry at all. It's not dependent on the equivalent bubble diameter of the bubbles within the reactor. So we use this to get a weight ratio of an acceptable range of the weight ratio for the surrogate fluid that we're using. So we're going to take the middle of this. So it ranges from 0.27 to all the way up to about 0.38 glycerol by weight. We then move on to further constrain the equivalent diameter by looking at the constraint of the Reynolds number from the molten salt reactor experiment. It's the weight of glycerol divided by the weight of water within the mixture.
Okay.
So you can express this by percent as well,
Okay.
by multiplying by 100. So we then graphed the acceptable range of the Reynolds number. So in the molten salt reactor experiment, the Reynolds number of the bubbles ranges from 1.97 all the way up to 4.2. So we found a constraint for an initial constraint for the equivalent bubble diameter, taking that into consideration, and that's 0.5 to 0.3 millimeters in diameter of these spherical bubbles. So in order to further constrain this equivalent diameter to see what is acceptable to use within the surrogate fluid, we applied the constraint of the Eötvös number, and finally we get a range of 0.35 all the way up to 0.365, which is a very tight window. It's about a variation of 5%. So we need a very precise way of injecting bubbles that are very small, like 0.35 millimeters. And we decided to do this through the use of microfluidics. There are three common microfluidic structures. These are the T-junction structure, the flow focusing structure, and the coaxial focusing. We decided to use the flow focusing structure shown in the schematic in the middle because of its high bubble generation rate, as well as the abundance of information of models controlling bubble size from the literature. We decided to go with the model developed by Liu 2022, or 2014 rather, excuse me, which relates the volumetric flow rate ratio and the capillary number, another dimensionless number, to the volume of the bubbles produced by the microfluidic channels divided by the width of those channels, assuming that those channels are square. So there are three important phases within the microfluidic structure. There's the dispersed phase, the continuous phase, and the two-phase flow region. So the dispersed phase for producing bubbles is going to be some sort of gas. The continuous phase is going to be some sort of liquid, and then in that two-phase flow region, you have bubble slugs. And so applying this to our model, we are using air for the dispersed phase, glycerin water mixture for the continuous phase, and then in the two-phase flow, we have a channel width of 0.4 millimeters. We decided to use 0.4 from the initial calculations with the with the Lu 2014 model to produce the bubbles that are at our target. So we color coded this. So the liquid is injected in, and this is a schematic of the chip that we designed. So the liquid's encoded with this dark blue color, with the surrogate fluid, and then the air is gray, and the two-phase region is this light blue. You can see that there are these 6 holes on the border of the microfluidic chip, and these are for our fasteners. We'll cover that very shortly. At the bottom, you can see a trial run of how this bubble injector is producing bubbles. So this microfluidic chip is made out of material called polydimethylsiloxane, or PDMS for short. We use PDMS because it is flexible and it's clear. It's also very valuable because you're able to cure it. So you can pour it into a mold to produce very small features. And it goes through a curing process. So you add this curing agent and you mix it up. And in that mixing process, bubbles are entrained within the PDMS material. And so you remove those by putting it into a vacuum chamber. Once the bubbles are removed, you pour it into a mold. We used a 3D printing process in order to create this mold. Recent advancements in 3D printing allows for us to create very small features within a 3D printed model. But as I discussed later, this wasn't the most precise process, and different manufacturing processes should be taken into consideration in future work. So we pour this into this mold onto a hot plate, which is set at 55 degrees Celsius. And we let it cure for a day. Once it's cured, it has a very rubbery consistency. So those channels are imprinted into it, but it has an open face. So we need to close these channels somehow. We do this by putting it up against an acrylic plate and applying pressure with fasteners. So a good way to visualize this sandwich is it's kind of like an Oreo, where the chocolate cookies are the acrylic plates, and then the soft cream is the PDMS material. And since this bubble injector is using pretty high flow rates of liquid compared to the channel width, it creates a lot of pressure. So in order to get a good seal, we use fasteners. At the beginning, we thought that the end condition, so that there are those holes at the end you can notice over to the right. We thought that we were going to get a good enough seal there, but we were getting leaks, so we needed some more fastener holes. I'll get to that in just a second. So in order to inject the surrogate fluid and the air into these microchannels, we need these fittings. So again, it's color coded for the dark blue being where we're injecting the liquid, and the gray being where we're injecting the air. So this is how we're applying pressure at that end condition. We use 2 more fasteners at the end to create nice, good pressure at every single stage of the microfluidic channel. And this is the setup that we used for the outside of the loop testing that I'll cover in just a second. We also need a way to connect this injector into the larger system, the system where we're actually testing how those bubbles move. And in order to do this, we fit this injector within this flange. So these 6 holes on the border of it are for attaching fasteners to the actual flange. We have this black O-ring to create a good seal with the overall test section. And the flange came in from the machine shop that we used, opaque, and it had a kind of rough finish. And this ended up actually creating some issues at the end condition, because when it's not very smooth, there's a lot of surface tension forces that create air pockets. So in order to smooth over this flange, we use sandpaper and acrylic polish. So here's a CAD model of how the injector is put together. You have the Oreo, the acrylic sandwich going into the injector, or into the flange rather, and using these screws to fasten it in and create pressure and lock down that end condition. And this is how the injector finally looked once it was finally constructed and put together. This is how the injector fits in with the test section. So we have a test section that's 1 centimeter by 3 centimeters. It's rectangular. You can see it at that top portion there, and it's secured to the test section with these 6 fasteners. So the surrogate fluid is stored within this 20-gallon tank seen in the image on the right here. That fluid is then pumped through a 1.5 horsepower circulation pump into the test section. We measure the flow rate through the test section with this flow gauge seen in the middle image. So before we actually put everything together and attach the injector to the flange and see how the bubbles are moving within the test section, we first need to test how is this injector working? How are the bubbles being formed? How big are they? So we wanted to get data straight from the source as they're being formed in the microchannels. So as you can see, we have the high-speed camera capturing the actual injector with the light behind it, and we tested flow rates between 50 milliliters per hour to 125 milliliters per hour. That's a very, very low injection rate. In order to inject fluids at that speed, you need something that it's very difficult to do with conventional pumps. So we use syringe pumps. So it's basically a syringe, and there's a plate in the back that gets pushed forward at a very constant rate. And so it was also of interest to us to know what the mass flow rate of the gas is. So since pressure isn't constant, and there's a pressure drop across the 2-phase flow region, and the outlet is atmospheric. So there's going to be a high pressure at the inlet. So we want to know what the mass flow rate is. So in order to determine the mass flow rate, we needed to know the pressure. So we have a pressure gauge from the outlet of the air injection site, but you can see that there are very discrete intervals of injection rates for the liquid, but it's not very intuitive for the gas. So we made a mistake in the setup of the syringe pumps. We didn't properly set the interior diameter of the gas injection syringe pump properly. So in order to correct this, we looked at what the actual interior diameter of the air injection syringe or the air injection syringe was, and we looked at what it was actually set at during our tests. And then using this equation at the bottom, we're actually able to correct that flow rate. The last 2 rows in this table show the superficial velocity of the 2 injections. So the superficial velocity is a lot more intuitive to look at when you're looking at pipe flow, since it shows you how quickly the fluid is moving through the pipe spatially rather than volumetrically. It takes into consideration the cross section of that flow. So from that setup, we got this raw data. Before we're able to do anything with the raw data, however, we needed to calibrate the image. We wanted to know how many pixels made up 1 millimeter of spatial distance. So in order to do this, we used a calibration sheet. Each of these squares is 1 millimeter wide and 1 millimeter tall. So we counted the number of pixels wide and tall each of these squares was to get a pixel to millimeter conversion ratio. With this, we were able to do some data processing. So this raw image, there's a lot of non-useful data within it. An image is basically a matrix of numbers, and so the smaller the matrix is, the less computational complexity you have. So in order to just look at our region of interest, we cropped the image. Once the image was cropped, we inverted it so that the lighter pixels were considered as bubbles, and the darker pixels were considered as empty space. We then saturated the image by making the We saturated the image to increase contrast. We then filtered out a lot of the noise, the small specks within the image, with a medium pass filter, and then we binarized the image. So we took the pixels, the top 1% of pixels, and converted those to value 1, corresponding to white, and then the darkest pixels, and we converted those to 0, or black. So these bubbles have a lot of empty space within them in this binarized image. We want to consider that the bubble is a continuous entity, so we closed the image and filled it. You can notice that the bubbles at the end conditions on the left and the right don't behave very well. They don't close properly. So we set a threshold of around 200 pixels. So any pixels that were within 200 pixels from the borders were not considered for our data processing. So with this, we calculated the average frequency of bubble generation. So we counted the number of bubbles that exited the frame and divided it by the total time of the test. And the total time of the test was the number of frames of that test divided by the frame rate. This only gives us an average frequency of bubble generation. This doesn't take into consideration the fact that there might be some fluctuations within the frequency. In order to correct this, we identified a second region of interest bordered in this red color here. And so for every single frame, we summed up the number of pixels within that second region of interest, and we plotted it as shown on the bottom left image here. And if that function is periodic, we know that we have a nice constant frequency of bubble generation. In order to validate that this is a periodic function, we did a Fourier transform on it to create the graph in the middle. This method of Fourier transform to validate the frequency is novel in respects to microfluidics. So if it did not pass this test, an example of this would be the image on the bottom right here with all sorts of noise in it. There's no clear dominant frequency. So with this, we're able to do a lot of very useful calculations, knowing that the frequency is constant and the dominant frequency equals the average frequency. So we took the ideal gas law to get the mass flow rate, and then we used a mass balance in order to know that the mass of the bubbles should be constant throughout the two-phase flow region. We calculated the average bubble mass by dividing the mass flow rate by the frequency, and we also got the average bubble volume by getting the volumetric flow rate divided by the frequency of bubble generation. And this bubble volume can be converted to equivalent diameter. That's what our target is. So again, it's just an average bubble volume that we got from that frequency analysis. We want to look at what the kind of variation of bubble volume that we get. So in order to do this, we had to figure out a way to create a 3D representation from a 2D image. So we went column by column for each individual bubble and counted how many pixels were in each column of that cross section. We also assumed that the cross section of the pipe was square, so the width of it would equal the depth of that channel, and so that would give us a circular cross section of the bubble at every single point. So in order to create a 3D representation, we stacked each of the columns as cylinders. So the diameter would be how tall each of those columns was, and then the height of that cylinder would be 1 pixel. So we use our pixel to millimeter conversion ratio for that. And so the assumed shape is this CAD model on the bottom here. And so from all this analysis, we got this following result. So we have equivalent bubble diameter on the vertical axis, the superficial liquid velocity on one of the horizontal axis.
Brady, this is Dr. Freeman. Can I interrupt you for a minute?
Yes, sir.
So So I know that you're building on previous studies, the model of doing the model of the 3D bubble on the previous slide. Is that building on previous work that has been done, or is that something new that you did in this thesis?
This method is new within this thesis. Previous studies have been using this average bubble volume and assuming that that is the same for every single bubble.
Okay. All right. Thanks a lot.
Yes, sir. So from this graph, we're able to see a general trend of how the equivalent bubble diameter changes with the superficial liquid velocity and superficial gas velocity. So as you increase the superficial gas velocity, we see an increase in the equivalent diameter, positive correlation between those two variables. On the other hand, when you increase the superficial liquid velocity, we get a decrease in equivalent bubble diameter. So negative correlation. And so in order to more intuitively visualize this, we took each cross section of that graph. So for each gas flow rate, we saw how the equivalent bubble diameter changed with the liquid flow rate. And so here we can see this more accurate negative correlation for each gas flow rate. Moving on, we can see how it changes with the gas flow rate by holding the liquid flow rate constant per graph, and then seeing how it changes on the horizontal axis with varying gas flow rate. We also got these results from the frequency analysis. So we saw how the frequency changed with changing the liquid velocity and the gas velocity. There's not a very strong correlation between the gas velocity and the frequency, but you can see as you increase the liquid velocity, we get a higher frequency. So now that we know that the bubble injector works as predicted, we want to see how it works within this larger test loop. So again, we controlled the injection rates with the syringe pumps. We used a pressure gauge at the exit of the gas injector or the gas syringe to determine what the mass flow rate is. We used a light shining on the test section and then a camera capturing the test section directly, about a foot above where the bubbles were injected. So again, we needed to correct the volumetric flow rate of the gas because the syringe pump was improperly set. And so this is an example of a raw image that we got from that data. As you can see, again, there's all sorts of there's unuseful information at the borders, so we cropped the image down. We then again we needed to calibrate the image. So looking at each of these squares, knowing that they're 1 millimeter, and counting the pixels within them to get a conversion ratio. We then obtained a background image by looking at the pixels that remained very similar from frame to frame. So we took 100 frames and we saw which pixels remained very similar within that. And then in order to invert the image, we subtracted the raw image from the background image to get this. We then, as said before, we saturated it to increase the contrast. We then ran it again through a median pass filter to remove any of the like tiny small bubbles or noise within the data. And then we binarized the image to convert all the pixels to either 1 or 0, corresponding to white or black. We then filled the bubbles to consider them as one continuous entity. And then we removed the bubbles that were more than twice as big as we expected them to be, or twice as small as we expected them to be. These bubbles weren't useful because we knew that they weren't coming out of the injector, or they weren't the size that were directly coming out of the injector. We then applied a circularity threshold, seeing how close each of these entities were to a perfect circle. And once we applied that threshold, we got our final image here. These are the bubbles that we're considering as data points. We then extracted the equivalent diameter of each of these bubbles. So we assumed that these circular bubbles corresponded to a spherical bubble in 3 dimensions. And when we plot the distribution of the diameter of each of these bubbles, we get this distribution on the left here. You can see that there are multiple modes of this. And what our hypothesis for the reason of the multiple modes here was the fact that bubbles would coalesce together, creating a bigger bubble. And then in order to validate this, we first smoothed this distribution with a built-in MATLAB function to get the distribution on the left, or on the right rather. And so we took the first peak from this smooth distribution, and we assumed that that was the size of the bubbles before any sort of coalescence. As soon as they come out of the injector, this is the size of the bubbles that the injector is producing. And so
this is Dr. Freeman again. So your last slide, you talked about screening out the big bubble sizes, and I was thinking that the reason for a big bubble might be coalescence, and I don't understand that now. This next slide, you're looking at bubbles you think may have coalesced.
So the big bubbles that were screened out here were from the bubbles shearing off of the air pocket on the side of the bubble injector. There wasn't a perfect seal within the flange and the test section, so there were some air pockets that formed, and these very large bubbles most of the time came from bubbles shearing off of that. That's something that should be improved in future work.
Did you observe that, or is that speculation?
It was observed.
Okay.
There was also, as mentioned earlier, there was when the end condition of that flange is rough, there is a propagation of surface tension forces that allow a air pocket to so say it's the flange here. If it's very rough, you can have a surface tension, so the bubbles kind of stick here, and so all that air injection rate is making a bigger and bigger bubble. It's not natural coalescence, so the bubbles come out and then they find each other, meet, and pop together. It's if like many bubbles come together.
So you were getting air pockets and then some shearing with those air pockets, and that was contaminating, I guess, your bubble samples, so to speak.
Right, yes. And so we know that these bubbles are not coming straight from the injector because of just how very big they were. In order for this to be a coalescence, it would have to be like 10 to 20 bubbles coming together. So
Okay.
that's not very useful data.
Can I follow question? What's
Sure.
the size of these bubbles? The ones the large bubbles that you eliminate?
It was an area threshold, so the ones that were moved. So have to do some mental math here, but what the threshold here was any bubble that was pi times the diameter 0.35 squared. Anything that was below half of that area was removed, and then above pi times about 5 or 6 or 0.5 or 0.6 millimeters squared.
So theoretically, I guess or experimentally, that the size of the bubbles that coalesce cannot be more than certain amount, right?
Yeah, it only has 12 inches from the point of injection to the point of observation. It's highly unlikely that 10 bubbles will coalesce together naturally.
I guess something like this supports your statement, if you can demonstrate that or estimate. You know what I'm saying?
We could track these bubbles through each independent image and see how they're moving. I mean, in these tests, the flow rate within the test section is making it so that the bubbles are moving at about like half a meter per second. So
So in
it only
principle, you
has
can't say how many
third of a
bubbles.
second
Yes.
to get from the injection point to the observation point.
So you potentially know that, actually. You can easily estimate it. That cannot be that size bubble.
Right, right. I don't have a specific model to prove that, but just by inspection, looking at the way that the bubbles are moving, they're rather far apart. This image is a very high concentration of bubbles for the raw data that we considered. I unfortunately don't have a
That's
better example of the bubbles being farther apart, but in a lot of the frames there were 0 bubbles. So they weren't very close. And so once we converted those bubbles to a volume and divided by the volume corresponding to the bubbles coming straight out of the injector, we get this following graph showing 3 very observable modes, one at 1, 2, and 3. And this gives very good evidence that at least for this test, the only reason that there are different modes would be from that bubble coalescence. And so from this, we get the following distribution of bubble diameter. It's a little bit tough to see the trend here. There are just over 1/4 of the data points in this test than there were in the outside of the loop tests. So noise is projected a lot. It's amplified. And there's also a lot of uncertainty. As I mentioned earlier, there are these air pockets. There could be bubbles being generated through the system in all sorts of different places. So that could offset the modes of that data. And that's what we got from that graph. Comparing these results, the size of these bubbles to what our target was, you can see that we are above the target equivalent bubble diameter. We were shooting for about 0.35 millimeters of equivalent bubble diameter, but we ended up getting around 0.4 to 0.6. And so the result here, we see that the target is in red, and what we actually got was in this green box. We're able to fix this by decreasing the width of the microchannels. I'll discuss that a little bit later. Seeing how our data fits with the model from the literature, going back to the LU 2014, we see that model vastly overpredicts our data. And our initial thought of why this is because this model assumes that we have a square cross-section of these microchannels. And we also observed that the pressure drop was greater than would be expected with a square cross-section. So using fasteners to increase the pressure on those microchannels to hold it together, prevent leaks, it actually our hypothesis was that it crushed these microchannels, making them rectangular rather than square. So in order to see what the new depth of this was, we used this following process. We assumed that the superficial velocity of injection equaled the velocity of the bubbles in the microchannel. So we tracked how far the microchannel or the bubble traveled from frame to frame to calculate the velocity. We assumed that this was the superficial velocity, and then we calculated the cross-sectional area of the microchannels from the superficial velocity. We then got a channel height from this cross-sectional area, and then we used a new metric for this. So the characteristic length of a square channel is its width, but for a rectangular channel, you have to define something different. And this is commonly used as the hydraulic diameter, as displayed in that equation. And then we took the same kind of general shape of that model developed by LU 2014, but we needed to find new constants. So constant alpha and constant beta were found through a grid search of along ranges that were that they would likely fall under. Once we found the combination of alpha and beta that created the smallest error, we found the shape scalar S by dividing the average volume of the bubbles from the data divided by the average volume of the bubbles from the model. And so once we did that, we get this new novel model that I developed myself. And all the data fits within 5% of the model. You can notice that this doesn't have any sort of dependency on pressure, and this is because it's looking at the volume of the bubbles as it's produced rather than the volume of the bubbles at the outlet. So looking at how this model behaves in comparison with the fluctuations in the liquid flow rate, we look back at that graph and graph the model on top of the raw data, and we see that the model fits that data quite well. Moving into gas flow rate dependencies, you can see that the model also performs very well across those dependencies. So when is this model able to be applied? So in our tests, we tested capillary numbers ranging from 0.0025 to 0.0062 and Reynolds numbers within these microchannels. It's not the bubbles Reynolds number as described before. It's the microchannel Reynolds number from 0.912 to 22.79. In addition to this, you can't just assume that if you have a capillary number and a Reynolds number within this range that it'll work properly. Certain flow rates will cause the injector to not work properly. So if the superficial gas velocity is too high, you'll get churn flow or annular flow. So these are different flow regimes within a pipe. You have bubbly flow, slug flow, churn flow, and annular flow. These microfluidic structures for flow focusing, it relies upon slug flow. So you need to have a combination of the superficial gas velocity and superficial liquid velocity that correspond into this slug flow region. We tested some flow conditions that were inside of the bubbly flow regime, and we found that the injector did not work very, very well at all. It created bubbles very periodically, and then it wouldn't create bubbles at all for a while. So we went this constant flow rate that we can predict very well. So we need to stay within the slug flow regime. And so looking at how this model performed with the outside of the loop test, we needed to figure out a way to see how the volume would change from the inlet to the outlet. And this is where the pressure ratio comes into play. So we took the pressure at the inlet from that pressure gauge, and then the pressure at the outlet was around atmospheric pressure. Multiplying our model by this pressure ratio gives us the size of the bubbles that are predicted to be at the outlet. And so this is how our model performs with the data from the inside of the loop tests. So to wrap things up, in this study, we created a way of generating bubbles with high precision and high frequency. The variance of the bubble diameter by percent was about 6% variance. The design can be used for all sorts of different microfluidic geometries. All that would need to change is you would need to use a new mold with different geometries, and you could use perhaps coaxial focusing or T-junction structure if you decided that you would like to modify it in that way. You can also very easily change the geometry of the cross section of the channels the same way. We also defined a new clear process of modeling a target system with an experimental system. So first you define the three-dimensional numbers, the Reynolds number, Yotvos number, and Molten number in that first system. And in order to replicate it, you vary the weight ratio of the glycerin water mixture and the equivalent diameter of the bubbles in your surrogate fluid system. That frequency analysis that we used was also new. So using that Fourier transform to ensure that we're getting a constant injection frequency, and then that frequency aligns with our average bubble generation frequency. Now, the cylinder stacking method was also new. That's never been done before, to get the variation in the size of the bubbles. That's how we calculated the variance of bubble generation.
Can I jump in and ask a question? So could you refresh me what the frequency was that you were generating bubbles at?
We were getting frequencies around 400 bubbles per second.
And what was your target or your goal for frequency?
In our initial design, we were getting we were assuming that using the capillary number and the Reynolds number, staying within those ranges from the Lou 2014 model would be sufficient. We didn't take into consideration that flow regime. So we were actually getting bubble generation frequencies about like 10 bubbles per second. Maybe up to 100, but we were not anywhere close to that. When we actually tested this, it only worked when we had higher air superficial velocity moving into the slug region. So we had greater bubble generation frequency.
All right. Let me just ask again, just because I'm just following this not necessarily understanding everything completely, but I guess you had what was the frequency you were generating, and then what was your target? And I know you just answered me, but maybe answer me more simply so I could understand better.
Our target was about 50, and we got about 400.
Okay, and then for bubble size, you used a metric, maybe the previous slide, like 6.8%. Was it variation? What was the metric?
So that was percent standard deviation. I misspoke, and I also put it on the slide improperly. So we took the standard deviation of all of the bubbles for each test, all the bubbles that were generated in each test, and we took the standard deviation of that number. We then we calculated the percent standard deviation by dividing that by the average of all of those volumes.
Did you present that in the text of the report?
I may not have. I saw your comment about that this morning.
Yeah, I mean, it seemed like a favorable number. So I was.
Yes, sir.
So in terms of bubble size, I'm just looking back at some of the earlier stuff that you were trying to hit a target, and your bubble sizes were a bit larger than what your target was. Is that?
Yes, sir. Yes,
correct?
sir. We were not able to create a combination of airflow rate and liquid flow rate that would result in a bubble that's that small. It would result into a bubbly flow regime, and this microfluidic injector doesn't work very well with bubbly flow regimes. It relies on slug flow.
And you showed that, I think you showed that in one of those figures that you presented, had a red square and a green square, and that was I guess the footprint of your work,
right,
against what I guess you were targeting the MSRAs. Okay, that makes sense. Thanks a lot.
Yes, sir. So, and then the model that I produced from all of this analysis was also new. It will require more polishing, but it has we have a very clear process of refining that. So looking forward, we would like to polish this injector so that it works exactly as expected. So in order to fix the kind of kinks we had in the system, we want to make the flange have a higher tolerance for where it's fitting in, so that we don't have these air pockets forming. We also want to make sure that it's flush with the test section, so that we get a nice seal. And we want to reduce the channel width in order to make smaller bubbles, so that we can overlap that green square and red square. We want to decrease the channel width, so that will allow us to stay within the slug flow regime, and also have these diameters that are small enough, so that we can replicate the MSRE system. We also had some problems with the precision of the channel geometry. The 3D printing process, while it is able to make small features, it seemed like it wasn't actually producing 0.4 millimeters by 0.4 millimeters. It's also very tough to validate that that's the case. Calipers can't really measure things that are that small very accurately. And so we also want to figure out a way to fix this problem of squashing the microchannels. One such way of doing this is to use glass as the plate to close the microchannels. Glass has a lot higher of an adhesion factor to PDMS than acrylic does, so it wouldn't require as much pressure from the fasteners. So we would get a more square cross section. We could also consider using laser etching in order to impress and imprint these microchannels into acrylic or glass, and then use PDMS as just a sealant rather than creating channel geometry. And so once we have a 100% functional bubble injector that's polished, that's creating bubbles exactly as we want them to, we can look at some bubble dynamics, seeing how these bubbles actually move. So how fast they're going, what kind of path they take, how much it varies from side to side. And once we have a really good model for this, we can very accurately get mass transfer tests too. So seeing how quickly air can diffuse into or different gaseous different gases that are dissolved in a liquid can diffuse into the bubbles. This can define Schmidt and Sherwood numbers. Machine learning can also be used for these dimensionless number definitions. So you can take the input of how fast these bubbles are moving and the kind of path that they're taking, and you can use that as an input, and it will give you an output of the Schmidt or Sherwood number, which is similar to, or the Sherwood number is very similar to the Nusselt number, which is for thermal diffusion. Here are my references. Thank you for your time and attention. Do I have any questions?
Very good. So very good presentation, course. I just want to give a general comment before we open the floor for questions. So course has done a pilot study. So this is the first time we are adopting this new design of bubble injector. Our previous injector was a very simple micro hose, which is about 200 micron. So there is not a good way to control the bubble size in the test section. So this is the first study. We are trying to precisely control the bubble size we generate. And then after Quartz finished his study, I think we have a PhD student, Liu Xie, Abra. He's gonna use Quartz finding discoveries and methods to continue research sponsored by DOE. So I think in that regard, Quartz has done a very good pilot study for the following work. All right, so I think do we have any questions from the general audience?
Go ahead.
Great presentation, Quartz. I really appreciate it and learned a lot. I wanted to go. I had a question regarding. You said that the injector worked best when the fluid was in slug flow, correct?
Yes.
by slug flow, do you mean that the fluid in the test section had to behave in that manner, or?
It's the fluid within the microchannels.
Okay.
So that the bubbles are taking up most of the diameter of the pipe.
Mhm.
And these bubbles in between, they didn't actually exist within the microchannel.
Yeah.
So this is what it looks like more within the test section.
Okay. Because it seemed like in the test section, this flow is very laminar,
Yeah.
right? But
Very,
in
very
a
bubble.
yeah, but in a would that be the same case in a molten salt reactor, or would the flow be even faster?
So
And how would that
in the molten
affect?
salt reactor, it's bubbly flow. We're trying to make the flow within our test section look exactly like it would within a molten salt reactor. And this microfluidic injector, it's not actually used for making the bubbles in the reactor. It's used for making the bubbles within our surrogate fluid system.
Thank you.
Can I ask you a general, or make a general comment, actually? So the bubbles are generated in a random manner, isn't? They're not deterministic. You don't know exactly the size of these bubbles. You have
know
an
exactly the size of
expected
the bubble.
value, huh?
Of
size of the bubbles.
bubbles from the injector or within the molten salt reactor experiment.
Well, your system right now.
So we have
It's not determined. It's not 100%. The size is
no.
so. My comment is actually, if you could come up with some sort of probability, and you could actually simulate this via something like Monte Carlo.
Well, so are you saying like getting a confidence interval of where?
Well, it's if you know some of the bubbles are generated certain way.
Mhm.
Based on your studies, you know the range. You
Right.
can fit a distribution to it.
For the inside of the loop, so like
The
fitting a
size of
distribution
the
this.
size of the bubbles. You have a distribution right now, don't you?
So
Yeah, you have
using
that's a distribution.
using Monte Carlo
Yeah,
on
you can sample
that
from.
smooth distribution function.
Yeah, you can or histogram, doesn't make any difference. You
Mm.
can sample from each one. And so in some ways you have a methodology with Monte Carlo to model this process and then compare it with your measurement, with your experiment.
Yes. Yeah, you could use Monte Carlo, but this was mostly to see if the.
I'm not saying you should have done it.
Yeah.
I'm just I'm just saying for the future work.
Right.
I think it would be very, very powerful to be able to theoretically effectively model this and compare it with measurement. And that way you actually, for the real applications, if you're talking about molten salt and so on, you could come up with a way to represent what actually happening in the system.
Yeah,
Anyway, I think
really
that's a
interesting. I
general
didn't think about
comment
that.
that for actually Dr. Liu and his future students, that I think something like this would be very, very powerful beside doing the measurements and experiments.
So, of course, I think you have, I remember you showed me the standard deviation of the bubble size, right, for each run. And you
Yes,
should
sir.
also have the distribution and histogram for individual run for, certain GAG and GF, correct?
Yes.
Yeah, so that's, I think, what Dr. Haggard was, suggesting. You could have a distribution for individual GG and GF, and probably use that for your as a simulation model for your inside of loop test.
Yes, yes, yeah. I mean, this is the distribution for the individual ones, and then the kind of with the error bars, the graph that I was showing you in our individual meetings, that was kind of showing the kind of the confidence that the actual that was initially calculated through the average rather than this first peak. So I didn't actually get a good confidence interval for the inside of the loop tests.
Yeah, that's something I think we can think about later in a future work. But in any case, do we have any other questions from the general audience?
There's nothing in Northern Virginia, I guess.
Okay.
Yes, I had a question.
Sure, yeah, that's up.
Yeah, that was a very good presentation, Quartz. I had a question about like how, what changes about your work when you scale your microchannels to a full size molten salt reactor?
So the microchannels aren't for producing the bubbles in the molten salt reactor. We really don't know as with the information that's available to somebody without a clearance. We don't know exactly how those bubbles are produced. We have a general idea from that schematic that it's very small flow rates of helium going through those tubes. Here, if I could pull up that schematic. It's so this microfluidic channel is really only used for the surrogate fluid system. It's not a proposition for using it in the molten salt reactor.
Yeah, so the bubbles generated in molten salt reactor is through a different mechanism. You have the bubbler here, right? You also have a molten salt jet. Actually, that jet impingement generate additional bubbles. So nobody has measured it, but previous research estimate the bubble size to be about I think 0.3, 0.4 millimeters.
0.4
This was an estimate.
Okay, so
We are trying to recreate that bubble size using
okay,
a
so the
different
bubble sizes
mechanism.
are the same. That's what I was wondering.
Yeah.
Okay.
Sam?
If you know,
We have one question. Go ahead.
Yes, so you talked about some of the changes to the experiment that in the future work slide.
Mhm.
But I was wondering about possible changes in the actual manufacturing of the test parts. You know, would you do anything differently now, or especially going forward into some of the future testing?
Of the test parts, like what do you mean, like the microchannel?
The beginning of your presentation, you talked about constructing the test plate and the Oreo and all that.
Right.
So would there be significant changes to that design, or do you
Yeah,
think
so for example, here we would use a width probably closer to 0.3 or 0.25 for these square channels. For the mold, we would have to change the mold for that. Yeah, so this is what I was talking about in the future work. That bottom plate, that's what the microchannels are pressing up against. That's made out of acrylic. Acrylic doesn't have a very good adhesion to PDMS, so you could use glass for that. And glass has very good covalent bonds with PDMS.
Thank you.
Yeah, I think we should move on.
so yeah, that's I think if you are general audience now, I think you will have to leave the defense.
Yeah, you guys have to leave. Yes. You have a system here. Okay, I think we are already here, but there are a few people that
Dr.
still-
Hagar, we still have several people on Zoom. I think
Yeah, I
but-
think, coach, you can drop them off.
Yeah.
Yeah, you can force them off. Okay, I think, Dex, yeah. Let's see. We have everybody out?
I think so.
Yeah, okay. Okay, go ahead.
So now it's the Q&A time for the committee members. I think in addition to the questions you have already asked, now it's more, tough questions that you may have. So that's